So today I'm going to talk about the instrumentation part of the EPR study. We can consider it as the second part of the instrumentation, because the first part we included and gone through in the last lecture. So today I'm going to talk about the generation and the detection of magnetic field. It means how we can generate the magnetic field during our EPR spectrometer, and what specific criteria we are taking care. Then we will talk about the optimization of the detector. The detector can simply get the power output, and how we can optimize, because there are some factors which are increasing the sensitivity of the detector. There are some factors which are decreasing. So we will have to take a midway or a particular situation where we have optimized the sensitivity and the loss. Then we will talk about the radiation losses and which unit we are using to describe them. Then simple spectrometer structure, then how we can modify it to increase the sensitivity. The modes we will talk about, and how we are coupling our cavity with the clusteron mode, and how we are going to change the window of the cavity, and I will explain later. So these topics I will include today. So how we are going to create the magnetic field. These two are the Helmholtz coil. These coil are actually the simple copper coil winding like a loop. So these are two loops. Basically, there are multiple turns in this loop and this loop also. There is a particular distance. This distance is not too much. It's maybe in centimeter or inches. And our fundamental goal is we need a very uniform magnetic field between these coils. To increase the magnetic field strength and the uniformity, we use a soft iron core inside these coils. And the dimension of this core, the ratio is not correct. Actually, these two rectangles should be in equal dimension. So these iron cores should include, or these magnetic lines should be going through these iron cores. The structure should be like this. So if we see this real picture of the EPR spectrometer, these two big circle or cylinder, these are actually Helmholtz coil, and this rectangular bar you are seeing, a very big bar, this is soft iron core. So this is the very fundamental structure which we are using for the generation of magnetic field. These are the pole pieces which you can see. This is the cell bar from which we are putting our tube, the sample cell tube. So I told you that the homogeneity of the magnetic field should be very good. The field lines between these coils should be very homogeneous. If we are using a magnetic field in the range of 3000 Gauss, the inhomogeneity should be less than 10 milligauss. That's the sensitivity which we should use when we are generating the magnetic field. And we use a simple Gauss meter for the measurement of field. We can use the Hall effect Gauss meter also, but because of the high sensitivity measurement, we use NMR Gauss meter. That's a separate thing. I can explain, if you will wish, that why we use the NMR Gauss meter in case of the measurement of the magnetic field in case of EPR measurement. So after the generation of magnetic field, we get the signals from the sample. Then we have detector. The detector will convert the microwave power, which is coming from the cavity, and it will convert the power into the electrical current. And as the detector, we use silicon diode. It's a very simple structure of the simple diode. It's a diode, a silicon diode, and it's a circuit diagram of the diode. This is the diode. We calculate the voltage. We get the current output. This is a variable resistance, so that we can exactly get the value of the current. But we know that the characteristic of the diode is not linear. So whatever current we are generating through this circuit, it's not actually linearly proportional to the received microwave power. So if we see the characteristic of the diode current, which we are actually measuring, and the microwave power which is falling on the detector or the silicon diode, it's not linear. It's linear for a particular range, then it's increasing exponentially. So if we take a microwave power in this range, in the lower range, you see there is no change in the diode current. But if we see in this range, if we take the microwave power in a higher range, there is a significant change in the diode current. So if we are taking the microwave power from the source in this range, the sensitivity is very high. A very small change in the microwave power which is falling on the detector will change a very significant diode current. It means our instrument should be working in this range, so that very small change will give us a good result or a significant result which we can measure. But there is a problem. If we keep on increasing the power of the diode will create a thermal noise, and that thermal noise may be very less in a lower range of the power. But if we keep on increasing the power, that thermal noise, this graph is telling about the that conversion loss. If the conversion loss is less, the sensitivity is high. So if we keep on increasing the power, the loss will be decreasing, but simultaneously the noise, the thermal noise of the silicon diode is also increasing. It means we should increase the power. We should be in this range. A minute change in the power is giving us the change in the current, but we should not go beyond a particular range when the thermal noise is too much. Otherwise, the sensitivity will be compromised. So we need a optimization where we have a particular high power, and simultaneously the diode is not creating too much thermal noise. Now, when we are talking about the losses, either it can be a thermal loss or it can be a radiation loss, which is coming from the source to the cavity and then to the detector. There are some losses are there, and that we calculate in decibel. So if P in is the power coming in and P out is the power coming out, we calculate in dB, like 10 log 10 P in by P out. So if we take that P in and the P out, the output power is 10 times less than the input power, then our unit will be 10 dB. Our loss is 10 dB. That's how we calculate the loss. We can calculate in milliwatt also, but this is a very convenient form. So we calculate 10 dB, 20 dB loss is there. So like that we can get, okay, 100 part is lost, 1/10 part is lost. Like that we can calculate in decibel. But the problem is we can calculate simply by the power in and by the power out when we are thinking about a simple waveguide, which is behaving in a similar way, like this power in is power out is maybe this is the 10th part of this. This is a reciprocal waveguide. So if we take it reverse, P in from here, P out from here, the loss will be similar, 1/10 here, 1/10 here. But there can be different types of non-reciprocating device, which is not a bad thing. We need non-reciprocating device in future, that I will explain later. In these type of devices, the P out or the loss in one direction is very less, but in the other direction, the loss is very high. It means the power out is approximately 0, or we can say that there is no power coming out in the different direction. So if we think about the same device here, we call it isolator. In this direction, the insertion loss is very less, 0.1 dB only. But if we go in the reverse direction, the loss is very big. It's 20 dB. We are calculating in decibel. We can calculate the absolute value of the microwave power in decibel, watt also, or milliwatt or watt, that we calculate when we take the power and we normalize it for the 1 milliwatt. So if we are getting a 20 dBm, it means the power value is 100 milliwatt. That's just a conversion which we are doing when we are just calculating the power output. This is the ratio. The last slide was the ratio of the power in and power out. but when we are calculating only the power out value, we can calculate in milliwatt also, and that's the conversion formula. Now this is the very simple spectrometer schematic diagram. This is a clusteron or the gun oscillator. This is our transmission cavity. We have put the north pole and south pole through which we will put the external magnetic field, and we have a detector. But if we are taking a transmission cavity, the quality factor or the quality value is very low. Why? Because it's getting the microwave radiation inside this, the standing waves will create. But if the leakage is too much, the standing waves will not give us a very high sensitivity, and the detector will not be able to detect only the signals which are coming through the sample. So the sensitivity is very low for the transmission cavity. So we use reflection type cavity, which I showed in the last lecture, that there are two types of cavities: reflection cavity, in which the radiation will bounce back from this wall, it will not go through. So we use reflection type of cavity in the new modified spectrometer. Now we use not just the transmission cavity. Before that, we also use circulator, and circulators are actually non-reciprocative devices. It means circulator have three holes or the three ways. We call it port. So we have three ports. This is the in port, or we can take it as the power is coming through this port. So one port, two port, and three port. The property of these ports are, if power is coming or the microwave coming through the one port, it will go to the second port. And if the power is going through the second port, it will go to the third port. Then it can go from the third to one, but the power will not go from the 2 to 1. It will never come back from 3 to 2. So what is the benefit that I will tell you? So we have used a circulator. The circulator has a property: the power can go from 1 to 2, it can go from 2 to 3, but it cannot go directly back to the source. So there the loss is very less in this direction. So the loss is very high in this direction. So the radiation will not go back to the oscillator or the source. It will only go to the detector. Because if we use a simple waveguide, when the reflection or the signal is going back through this channel, it can go to the source also, it can go to the detector also. But we don't want the signal to go to the source, we only want to go to the detector. That's why we use circulator, which is non-reciprocative device. The only one channel is open, in which the loss is very less. If we go reverse through the same channel, the loss is very high. Simply it will not take that path. In this way, the signal will only go to the detector, and we are not losing any signal through this circuit. So this is a including device which we include in our modified new EPR spectrometer. Now the clusteron or the source has a mode. It means the power output depend on the frequency of the reflector voltage. This reflector voltage is actually the voltage which we can vary, or we can vary the frequency of the source. So this is the power output which we are getting in at our detector. This is the reflector voltage which we can manage from the source. In this way, in this case, I have imagined that there is no cavity. There is no standing wave generation. There is no absorption from the cavity. In this case, the detector is detecting a absorption from the cavity also. So this signal is actually coming because the cavity has absorbed some power from the source. This depth will not change if you will carry on changing the reflector voltage or the frequency. Only the position of the what should I say, valley will change. And this is the iris tuning which we use to change the depth of this value. So why this is important? This is important because when we are detecting the signal, we need the maximum power output. It means we need this signal to be here. So there are two important parameters here. First, the frequency of the source or the reflector voltage, which should be somewhere here so that the power is maximum. The second, the frequency of the matching frequency of the cavity so that this dip should be here. This line is telling about the zero reflection. It means if this dip will touch this line, there is no reflection. The cavity is absorbing everything. So there are three modes we can say. There is critically coupled. In critically coupled condition, the reflection value, the reflection power from the cavity is zero. In this case, it is overcoupled, and this case it is undercoupled. In undercoupled condition, there is some reflection power from the cavity which is going to the detector also, along with the other signal. One thing is important in this case also. When we are detecting the signal, yes, in this case. In this case, we have seen that when we are having a very low microwave power, in this range, the sensitivity is very less. The change in the power will not giving us any signal, or the diode current is not changing. It means we need more power. In this range we need. So what can we do? How can we change the microwave power, or how we can go from this range to this range? This thing we can do when we are doing the coupling. What we can do, if we think about this condition, some part of the power is reflecting back to the detector. This power we can use as the bias power, or we can go from this range to this range. It means this change from here to here, this microwave power we are getting from the reflected power from the cavity. 100% there is a slightly loss of the sensitivity here, but that will be compensated from the sensitivity increase when we are having this range. It means we don't need a very critically coupled, we can have a very minute undercouple. If we are taking a very minute undercoupled condition, we can have additional bias microwave power so that we can get a better signal and a better change in the diode current. But we cannot have a lot of variation. It means the power, the radiation reflected here cannot be too much. Otherwise, the matching will not be good. So what we do, the second thing which can contribute the power so that we can get the good range where the sensitivity is more, we can take the additional microwave power directly from the source, not from the cavity, but directly from the source. So we use a phase shifter. This phase shifter is so that the phase which is coming from the signal, and if we are taking directly from the source, that will match. That's why we are using a phase shifter. And we will use a bias power which is giving us a very minute change in the power directly to the detector so that we can get this range. It means this difference which we want, this we will get directly from the source. We will use a phase shifter which will match the phase from the signal and the source, and this difference which we want to get a better signal, we can achieve not from the cavity. We will not compromise with the sensitivity. We will directly get it from the source. So that's how we can increase the sensitivity of the detector. In this manner, we need not to play with the diode thermal properties also too much. We need not to play with the cavity properties also too much. We can get a critically coupled or very critically coupled condition also, because in this way there are some radiation loss is there, the properly standing waves will not be created. So this is not preferred. So nowadays, in the new systems, we use a phase shifter and a bias power directly from the source, and then we feed it to the detector so that we can get a proper situation for the sensitivity. So thank you. This was all for today.